Hello everyone, welcome to this video looking at the limit of a function. So in the last section, we looked at the tangent problem and the velocity problem, and hopefully we were motivated by that to study limits. For instance, when we looked at the problem of finding tangent lines, we had to look at slopes of secant lines from P to Q, and then we had to look at what happens as Q got closer and closer to P. And if that settled down to a pattern, that gave us the slope of the tangent line. But we could never just plug in Q equals P because then we would get 0 divided by 0 and it wouldn't make any sense. So based on that, we had to study these things called limits. So now we'll look at the definition and do a couple of initial examples based on that. Okay, so let's look at what the definition is. So let's suppose we have a function, f of x, and let's suppose it's defined close to a number a, but maybe not at a. So we don't care at all about what happens at a. It might be defined, it might not be defined, okay? But it's defined for every value of x which is close to a. For instance, 1 over x is defined close to x equals 0. Okay, so here's the definition of a limit. So suppose that we can make the values of f of x arbitrarily close to a number L. So in different examples, we're going to have different numbers. L is just a number. So suppose we can make f of x as close as we like to L, or arbitrarily close to L, by making x sufficiently close to a, but not equal to a. We don't care at all about what happens at a. So if we can make the values of f as close as we like by making x sufficiently close to a, then we say the limit of f of x as x approaches a is equal to L. So we'll see what that looks like in a picture in a second. But since we don't want to write out this long sentence every time we have to do this, there is a piece of notation. So we have this notation, limit as x tends to a of f of x equals L. Or alternately, we can say f of x tends to L as x tends to a, just depending on which is simpler to write at that moment in time. Okay, and if there is no number L where this works, then we say the limit at a does not exist. Okay, so different examples will have different numbers L. If there is no L at all where this makes sense, then we say the limit does not exist. Okay, so to just say that again, if we can make f of x as close as we like to a number L by making x close to a, then we say that the limit of f of x is equal to L at x equals a, or as x tends to a. Okay, so here is a picture, a rather crude one that I drew myself, but hopefully it will be clear what's going on. So we have some function y equals f of x, and it doesn't have to be any function we've seen before, it's just some picture I decided to draw the graph of. And it's very nice and smooth, and it's defined everywhere. So here I picked a point A on the x-axis, and when x equals a, the graph is very nice that f is equal to the number L. And f takes this value here, so it's a natural value. It's all smooth, all joined together. And here I claim that in this picture, the limit as x tends to a of f of x is equal to L. Why is that true? So if we think back to the definition on the previous slide, what we just said is that we can make the values of f of x as close as we like to L. So what does that mean on the picture? It means that, remember L is the y value or the number on the y-axis. It means that if we draw this narrow band around L, or however narrow a band we decide to draw, so here is this band around y equals L, we can make the graph of the function lie inside here, provided we make x close enough to a. Okay, so here if you want to be inside this blue band around L, then you can do that provided you make x belong to this band around a on the x-axis. Okay, and as you can see, if I'm in this interval, then I will be somewhere between here and here, so the graph will definitely be in this band around L. And remember we said we can make, the definition is that we can make f of x arbitrarily close to L. So I can shrink this band as small as I like, and the same thing should be true, right? If I make this band even smaller, if I draw the dotted blue lines closer and closer to L, then we can still make sure the graph lies inside those dotted lines, as long as we make this interval around a just a little smaller, right? If we keep making this interval smaller and smaller, then we're going to be inside these closer and closer vertical bands around L. So whatever vertical bands you choose, or whatever bands you choose around L, you can make a small interval around A so that if you restrict to that interval, then the graph is going to stay inside those bands. Okay, so this is the limit as x tends to A, f of x equal L in a picture. Okay, but remember we said we don't care what happens at A. So here at A, the function is equal to L, everything is nice, right? The function is arbitrarily close to L, even at x equals A. It's a very nice picture. But the same is true in this picture, right? Still, we have the limit as x tends to a f of x equals L. But in this case, the situation is different, right? So this picture is exactly the same as my previous picture. All I did is that in the previous picture, the value at a of f of x was equal to L. It was up here, so this was called in. Whereas in this picture here, I have a hollow circle, and here I have a filled circle. So all that means is that at x equals a, the function is defined to be equal to 0. okay? Or even in some other examples, the function might not even be defined at a. So it's not an unnatural thing. But still, in this case, the limit as x tends to a of f of x equals L. Why? Because if we think back to the definition, we can make f of x as close as we like to L, to this number here. Whatever band we pick around L, we can make the graph lie inside, provided we make x close enough to a. So provided we stay inside this band around, or this interval around a. And that works however close we want to be to L, right? If I was going to make it very, very close like this, then I would just make a very, very short interval around a. So the same thing is true, even if at x equals a, it's very far away, right? At x equals a, it's down here. We don't care at all. With limits, we don't care what happens at the function value, okay? Okay, so how do we find limits? So at the moment, I didn't really give you any tools, so the best we can do right now is to guess based on calculations. All right, so let's see a couple of examples where we calculate and we try to guess some limits and maybe confirm in a picture. But as we'll see, there are going to be limits to using calculators. That's an unintended pun there. Calculators are not always great, as we'll see also with a couple of examples later. And we'll have more tools for calculating limits after that in the next few sections. Okay, suppose we have this simple example. We want to guess the limit as x tends to 2 of the function x cubed minus 5. Okay, and we said with limits, we want to see what value the function approaches, if any, as x tends to 2. So let's plug in some x values, which are close to 2, and see what the value of the function looks like. So we substitute some values. So we plugged in, let's say, 2.01, 2.001, all these values. You can hopefully trust me on the calculations. And as you can see, as we get closer and closer to 2, the function value gets closer and closer to 3 on either side, right? If we are a little bigger than 2, okay, it's a little bigger than 3. If we are a little less than 2, okay, it's a little less than 3. But as we get closer and closer to 2, the function values are getting closer and closer to 3. So we would guess the limit to be equal to 3. Okay, and you might say, this is a very, very simple example, x cubed minus 5. Well, if I just plug in 2, I get 8 minus 5, I get 3. So in that example, plugging in just works to find the limit, plugging in the x equals 2. And there are going to be a category of examples where that does work. Those are going to be called continuous functions. And then there are also going to be lots of other examples, mostly maybe they're the most interesting ones where that doesn't work. Okay, so here was the previous example in a picture. So we had y equals x cubed minus 5. The graph looks something like that. We guessed that the limit as x tends to 2 was equal to 3. Okay, well, that's true based on the picture as well, right? If we draw however small a band we want to make around y equals 3, around 3 on the y-axis, we can make the function value stay inside that band, provided we make x close enough to 2. Okay, and if you make this band around 3 smaller, everything will be the same, except you have to be all the closer to 2 on the x-axis. So the picture confirms our calculation. Okay, so let's look at some non-obvious limits where we can't just plug in. Okay, so let's try to guess the limit as x tends to 0 of sine x over x, if it exists at all. And clearly we cannot just plug in x equals 0, because if we try to do that, on the top we will get sine of 0, which equals 0. And on the bottom we will get x equals 0, so we will get 0 over 0. And remember that for mathematicians like me, 0 divided by 0 is a nightmare. I cannot do anything with 0 over 0, right? It doesn't make sense. Okay, so we cannot do that. So this function is not actually defined at 0. Okay, so nevertheless, let's substitute some values of x which are close to 0. So starting with plus or minus 1, but that's not very close, so we have to go closer. So plus or minus 0.1, plus or minus 0.01, plus or minus 0.001. Okay, trust me on the calculation. And you can see as x is getting closer and closer to 0, so either from the positive or the negative, sine x divided by x is getting very, very close to 1. Okay, so based on that, it's not a proof, but based on that calculation, we might guess that the limit of sine x divided by x equals 1. And actually, that's true. Okay, but here substituting didn't make sense. So there are going to be some simple examples where substituting does make sense, and we'll understand later which ones those are. But there are also going to be a lot of examples where you cannot just substitute. So it's really important with limits that we don't care what happens at the value that we're taking the limit to. We have to look at what happens for nearby values of x. Okay, so those were two relatively straightforward examples where we could use calculators. Let's look at some examples where calculators lead us astray. And we're going to have tools for avoiding relying on calculators a little later. So one example could be rounding errors with calculators. So if we look at this function, the square root of t squared plus 9 minus 3 divided by t squared, let's try to guess the limit as t goes to 0 of f of t, if it exists. Okay, limits don't always exist. Sometimes they do, sometimes they don't. We'll see in a little bit an example where they don't. So let's try to guess the limit. And as before, we plug in, just like the last example, some values of t which are close to 0. And if we plug in 0.1 and 0.01, it looks like we're getting very, very close to 0.1666 recurring. But then if you really want to confirm that, you should plug in a value of t which is very, very, very close to 0, as close as possible, and keep making them even closer. But if you do that with, say, seven zeros followed by a 1, if you plug that in your calculator for this function, it seems like you get 0, or the calculator, depending on how good your calculator is, it will spit out 0. So what is happening there? The problem is that with rounding errors, if you plug in this number, the top is going to be very, very close to 0, and the bottom is very, very close to 0. And the calculator, because of rounding errors, it's going to interpret the top as being 0. So then you're going to do 0 divided by something, and it's going to give you 0 due to the rounding errors. So here is an issue with calculators. So in this case, the correct limit is actually the one that we had before. It's 0.16666 recurring, so that's 1/6. And we'll see examples for doing that later. It will be rationalized in the numerator, I guess. Okay, another possible problem with calculators is that in all the examples before, we were just computing a bunch of values, plugging in some values, seeing what happens to the output, and then making a guess based on that. But a couple of values aren't always representative of what's really going on with the function. So let's look at sine of 1/t and try to guess the limit as t goes to 0 if it exists. And just like in the previous examples, right, if we're trying to guess the limit of a function as t goes to 0, we should plug in some values of t close to 0. And there are no distinguished values. We were just looking to see what we have. So let me just choose some values of t. And I'm going to choose them so that I can make a point with this example. But remember, to really have the limit as t goes to 0, you would have to consider all values of t which are close to 0. Okay, so let's look at, say, 1/2 pi, right? 2 pi is a reasonably big number. It's somewhere around 7, or somewhere between 6 and 7. So 1/2 pi is a small number. It's pretty close to 0. If I do f of 1/2 pi, well, f of t is sine of 1/t. So if I do sine of 1 over, and t is 1/2 pi, then the 1/overs are gonna cancel, and I get back sine of 2 pi. Okay, and as we all know, sine of 2 pi equals 0. So f of 1/2 pi equals 0. Okay, and then I'm supposed to choose numbers of values of t which are closer and closer to 0. So let me consider 1/4 pi. So 4 pi is bigger than 2 pi. 1/4 pi is smaller than 1/2 pi. So this is closer and closer to 0. And if I do f of 1/4 pi, I'm going to get sine of 1/4 pi. So I'm going to get just sine of 4 pi. And okay, sine of 4 pi equals 0. Okay, and I can keep doing that. F of 1/6 pi would be 0 by the same argument. Okay, but so this is with even multiples of pi. So let me instead choose some other values. So let me start off with 1/pi/2. Okay, pi/2 is 1/pi/2 is not very close to 0, but let's just see what we have. In a moment, I'm going to have some values which are close to 0. If I do f of 1/pi/2, remember f of t is sine of 1/t. So when I plug in, I'm going to flip. I'm going to get sine of pi/2, and sine of pi/2 is equal to 1. Okay, but I wanted some values of t which are close to 0. So let me consider f of 1/pi/2 plus 2 pi. Okay, so if I think of pi/2 plus 2 pi, it's a pretty big number. 1/pi/2 plus 2 pi is a pretty small number. So plugging in this makes sense. And remember, once I plug that into sine of 1/t, it's going to flip this. So I'm just going to get sine of pi/2 plus 2 pi. And that's 1, right? Remember, sine is 2 pi periodic. Sine of pi/2 is 1. So this is going to be 1. Okay, and then I want to choose numbers which are really, really close to 0 to insert. So let me choose this kind of rigged value, 1/pi/2 plus 2020 pi, right? So 2020 pi is a really big number. I add pi/2 to it. I get a really big number on the bottom. 1/that is going to be a really small number. So I'm plugging in a really small number into f. Sine of 1/t flips that, so I get sine of pi/2 plus 2020 pi. Okay, and then sine is 2 pi periodic. Here I have an even number of pi's. So I'm going to get the same value as sine of pi/2, which is 1. Okay. So if we look at what we did, we plugged in some values of t, which we could plug in 1/2n pi, for instance. There's a pattern. There are some small values of t getting smaller and smaller, as small as we'd like, for which it looks like sine is 0. And then there are some other values that we can plug in where it looks like sine is 1. Okay. So is the limit 0 or 1? And the answer is the limit does not exist, because remember when we talked about limits, there was only one number that could be the limit of a function at a given point. So what would it mean for L to be the limit of f as t goes to 0? So we're trying to understand the limit as t goes to 0, f of t. And it should be there should be a number L, or if there is no number L, which is the limit, then we say the limit does not exist. So in this case, there is no number L because what that meant was we can make the values of f as close as we like to L by making t close to 0. But in this case, we can't do this, right? If we try to choose L equals 0, there are always going to be some values where the function is 1. And if we try to choose L equals 1, there are always going to be some values close to 0 where the value is 0, which is not close to 1. So in this case, there is no L that we can choose. So let's see what that looks like on a picture. So here's the graph of y equals sine 1 of x, which is commonly called the topologist's sine curve. And we look at what happens as t is getting smaller and smaller. So sine of, or as x is getting smaller and smaller, so sine of 1 over x, it keeps oscillating between 1 and minus 1, 1 and minus 1. And it does it faster and faster as we approach x equals 0, okay? So if we try to choose a number as the limit, remember we were trying to find the limit as t approaches 0. If we would try to prove that or try to show that some number is the limit, suppose I want to have the limit equals 1. Remember that what that meant for the limit to be equal to 1? It meant that I have to be able to choose this thin band around 1. And I need to be able to make the function stay inside that small band by making x close to 0. But in this case, I can't do that because however close x gets to 0, it's always going to go down here, which is outside my band, right? It's not going to stay close to 1. And the same thing over here. Whatever L I pick, if I pick a different number, let's say I pick -1 or I pick -1/2, say, if I pick -1/2, just arbitrarily, if I pick -1/2, the limit definition would say, okay, my function should stay inside a narrow band around -0.5, provided I make t sufficiently close to 0. But that's not possible in this case, right? It doesn't settle down, it just keeps going up and down. So this is an example of a function where at x equals 0, it doesn't have any limit at all. Okay, so, and I should attribute that picture to the place online that I took it from. So thanks very much to those people. Okay, so just as a summary, today we talked about, or in this video, we talked about the definition of a limit. The limit as x tends to a, f of x equals L, it meant that we can make the function value as close as we like to L, provided we make x sufficiently close to a. And right now we don't really have any tools for doing that. One way is using a calculator, which is possible, or we could look at the graph. But there are problems with calculators, for instance, rounding errors, or if we just look at a couple of values, it might not really be representative of what's going on. And not all functions have limits. And also plugging in doesn't always work. So we really need to get to grips with limits. We need some tools. There's something worthy of study. They're not just something trivial. Okay, that's all for now. Thanks, everybody. See you next time.